St. Claret College, situated in North Bangalore of Karnataka state in India, aims to create an informative and sensitive future citizens through Claretian mission of education.
At St. Claret College, the focus of our education is to form individuals of character and integrity. Individuals who would become agents of social change and transformation. And for that to happen, we will certainly provide our students well-rounded education.
Situated on a serene and picturesque campus in the Garden City, Bangalore, we provide world-class state-of-art infrastructure and facilities to our students.
Our graduates become critical thinkers. Our graduate becomes individuals who are really very creative. And that happens when we provide them with an engaging curriculum. A curriculum that certainly responds to the needs of the industry, responding to the needs of the times.
Claret Group of Institutions caters to a large number of students, more than 9,000 in its campus, enabling them to understand and learn together to become thought leaders.
We believe in education that is inclusive and socially just. So Claret College has been offering education at an affordable cost to help and support everyone's aspirations.
Holistic growth of students is the core of our educational mission.
The education that we offer is faith-based Catholic education. And at the same time, we know the term Catholic literally means universal. And our education is inclusive. Our classrooms certainly represent the diversity of culture, diversity of languages, diversity of belief systems that India represents. And we offer our students the best so that they become global citizens.
Welcome to Claret College, the abode of knowledge.
Hello, everyone. I welcome you all to day 4 of the AI Workshop 2021. In the past 3 days, we had some amazing sessions with some great speakers, and continuing the momentum today, we have Dr. Rasif Rana with us. I would like to introduce Dr. Rasif Rana. Dr. Rasif Rana is the president of Exalt Solutions at Hexagon. Based in Switzerland, he manages the Exalt Solution business globally. He has extensive experience in developing scalable business. Sorry about the disruption. He has extensive experience in developing scalable business solutions for smart factories, construction sites, agriculture, and mining. He is a true technologist with a keen focus on digital business and its exponential growth. With hundreds of deployed solutions that are powered by Exalt, he is certainly the person from whom we can learn about the journey from prototyping to productization of business ideas. I invite Dr. Rana to take over the mic and share his knowledge and experience. Over to you, Dr. Rana.
Thank you very much, Bharti. Can you listen to me without any issue?
Yes, you are very audible.
Perfect, thank you. Hello, everyone. It's my pleasure to be here today with all of you to discuss this really important topic that we see from the business angle as one of the key decisive factors that can define really success or failure of a prototype, let's say, when it transitions to the product. So I'm glad to be here today with you. I work at Hexagon Exalt Solutions. Hexagon is a global technology company where we work in different areas, in different industry verticals, and our functioning operations and also our R&D in many countries of the world, and we are present in more than 50 countries. So I'll go ahead now and start my presentation. So let me share my slides. Give me a second, please. I'm getting some rights to Zoom. I'm sorry, I have to restart Zoom to give access to screen sharing, so I'll be back in a second.
Sure, no worries, Dr. Rasif.
Mm-hmm. Can you see my screen?
Yes, sir. Yes, sir. You are audible. So it's visible.
Excellent. So let's get started, and sorry about this disruption here. What we are going to discuss today are some of the key ideas. First of all, I'll share some words about Hexagon, what we do, and then we'll right away jump into the one example that I brought here that explains how we moved from prototype to a final deployment for one concrete use case that we just deployed. And there, we'll go through different stages and how we ended up into the final solution and what are the learnings that we, had during this journey. Also, some best practices. I'm also going to share at the end of it some of the key, let's say, positioning ideas that we do when positioning AI into the solutions. And then we'll have some final words on, the whole picture and kind of a big picture view at the end of it. All right, let's get started. So Hexagon at a glance here. As I mentioned, we are a technology company really driven by innovation. We invest about 12% of our revenue in the R&D globally, have more than 5,000 employees, part of total workforce of 21,000 employees globally. That are, these 5,000 are really dedicated to R&D. We file a significant number of IPs every year and have thousands of active patents on the technology that Hexagon has produced. As I'll mention to you in the next slide here, we really are relevant in the industries where we serve just because of the innovation. So where we go really from the, from manufacturing and construction industries into also, smart cities and also digital enterprises and reality capture, smart maps. That's whole spectrum of the technology that Hexagon develops. On its own, we have, started really some major revolutions, for example, in smart city. And that's how we stay relevant in the business and, go more and more kind of vertical into our customers' businesses, collaborating with them and developing the solutions together. From the stability side, the numbers kind of speak for themselves. Hexagon has been growing consistently over the last 20 years, from a $500 million company, say in 2000 to now we are closing in 2021, more than 4 billion euros. So, that shows that it has a really consistent growth there. And really our role is increasing in customers' businesses because, we find the only way to succeed and also to bring value is to understand the customers and integrate with their businesses. On the sustainability side, we take the sustainability story really seriously. First of all, the solution that we provide are really enabling the data for the environment, especially in the case of smart cities, but also in governance and increasing the social impact, literally unleashing the data for the greater good of the society. More concretely, Hexagon has also started in 2021 a key initiative internally. We call it our evolution, where we would like to now become completely carbon neutral. And here is kind of an overview that you can see here. On one side, we have the reality capture devices and positioning as the key technology that you see on the left side, where we are also innovation leaders there in capturing the real-time data. That's also kind of the pedigree of Hexagon because we come from the sensor world. And on the other side, we have invested heavily in the last 10 years on design and simulation to really kind of combine these two worlds together in the form of a portfolio for autonomous solutions. That's where we can then leverage data coming from the hardware on one side, but also then we can do design and simulation on this data and really kind of enable the autonomous technologies. Okay, so that was about the company, and now we directly jump into the customer that I would like to kind of walk you through the story and learn, together what we can from this journey. As my role is business, I manage the full business of Exalt Solutions. So the whole talk will be more towards the value creation and really kind of the business impacts and how, when a prototype transforms itself Hello, can you hear me? I think there was some interruption.
Yes, Dr. Rasif, you are audible.
Can you please let me know where I was interrupted so I can repeat a bit?
Just a
Yes,
second.
Dr. Asif, you were speaking about knowing the customers.
Okay, thank you. So yeah, as I said, it's quite important to have the customer there, and also to understand that. So this is the customer here. As I mentioned, these are the industry that the customer is active in. It's quite mid-sized company with around $2 billion annual revenue, and they offer vertically integrated solutions in recycle resin business, but also in general in the packaging industry. Have more than 60 plants worldwide, and more than 3,000 employees. So quite a significant, an interesting customer profile here, where we need to kind of bring this idea that I'm going to mention into production. So where we started was that we started looking into the the pre-digitalization stage of this customer, and by this I mean that we went in there and they kind of started discussing what's happening there. And
Dr. Asif,
yes.
sorry to interrupt. I think you have to reshare the screen.
Oh, sorry. Can you see that?
Yes, it is back.
Yes.
Thank you.
Yeah. I apologize. We work mostly with Teams, and Zoom is really kind of new for me. But here we go again. All right. So as I mentioned, we are, in this now, what we are doing here is we are in this very initial stage where the idea is, with the customer, how we can digitalize their operations. And we do different workshops with them, and also sit together. Stakeholder management and also stakeholders is a big story here, that really everyone who wants to take their product to, turn the prototype into product, they have to really think about. So this is the result of initial discussion with the customer, just to capture the kind of state of the affairs where they are. For example, the customer has this entirely paper-based process to capture the downtime. There is a production floor. So let's say bottles are being produced there for packaging, let's say for food and beverage, and the production line goes down. There is some problem that has happened there, and now there's no more production happening. This whole process, we understood that it was completely paper-based, so very, very cumbersome. And then when this downtime event happens, then someone captures this information in the form of a paper, and then normally they have to go and look into downtime codes. What is it? Is the motor not working? Is, for example, conveyor belt not working? Is there some problem with the blow molding, for example, when the bottle kind of gets created? Where is this whole thing? So there's really a kind of long list of downtime codes that you have to capture and put this in the paper-based process there. Very, very error-prone process, as you can imagine. But if you go there, it's not something that you can immediately see. That's the whole idea about creating a valuable prototype for the end customer, where you have to sit, where you have to map the problem, define the kind of the business process where it is touching, and then you can capture the problem first. So that's kind of the first result of the discovery workshop that you do, and then we found out, okay, so there is a problem with the downtime timing. In a similar way, we've identified yet another problem there, which is the overall equipment effectiveness, the so-called OEE. And OEE was even a bigger problem in this situation here, where the bottles are being manufactured in different production lines, but then the only KPI that's being measured is how many produced bottles are effectively loaded onto the trucks. and then also compare it to only the time that the shift is active. There is no information in the meantime, how, for example, or data for that matter, how, for example, it is going through, different production stages, who is going to kind of actively check that, and how this whole PLC data, for example, or IoT or connectivity data will be gathered together, and how this whole thing will work there. There is absolutely no insight there. And then leadership is blind towards the true performance of each plant. And again, we identified that's a one major area where we can now, first of all, go creating a prototype and then, go to a product. I see a hand raised by someone. So should we take some question, or is it like I can continue?
We can take the questions after your session, Dr. Rasif. You can continue.
Excellent. Thank you. And then two other ones, which are equally important there. We understood that, so think about it, that there is this, full production line there, and this production line has production going on. And now you have to do preventive maintenance there. And the customer is also very interested in going, for example, predictive maintenance. So you have these two elements of maintenance where things are going to fail, but you need to kind of, prevent it first of all, and then also predict it. Again, there is no digitalization there. The data collection is absolutely manual, no automation there. And also the information is not being shared. If something is down, then the maintenance needs to know during the shift, but it's only captured at the end of the shift. And so on. I have another example here, which is the computerized maintenance management system. Let's say something is breaking down, and how this whole work order process will start there. And then who will kind of come in and then, implement that process, and who will assign the technicians. So you can see here, it's really a mix of all these elements there, where on one side, the customer leadership is completely not, into the loop on what's happening. On the other hand, what's happening on the production floor is also completely disconnected from each other. And, everything kind of being captured two times. First time, when people are entering this data in this different, let's say, segments of the problem. And secondly, when someone then takes this data and feeds it into the Excel sheets or whatever was there. So this can show you a very important part of the prototyping, that first of all, it has to be discovered. It has to be discovered, it has to be mapped, and only then you can go into the second stage, into what to do about it. So we move on now. So this is another stage. So I'm only going to dig deeper into the first one, because otherwise this whole solution is too large. But for the sake of kind of learnings and how to do this journey, I'll only be focusing on the old downtime tagging and just explain, show others as the final stage. But the real journey will only focus on this one. So here is what we call that business process mapping. And this is absolutely true for all digitalization projects. Wherever you want to use data, and to digitalize a project or some operation there, you have to do this capturing there. So as I mentioned, we discovered first of all the problem, and then we mapped it. So once you map it, you would see that on one side, let's say the machine breaks, and then immediately production stops. And now the operator opens this, big binder or manual there, and it goes through really each one of them and find out, what has happened there. And then it identifies the codes for them. And then it puts this code into a paper sheet, which is captured after the, shift, and then it goes into the business objects. And then in those objects, then some kind of a very rough kind of KPI is calculated there. And while this whole thing is happening, maintenance, which is another function, is completely unaware that what has happened there until the end of the shift. And then it writes the machine failure code and also timestamps it. And then it goes, all this information goes to the supervisor, which then goes into the backend system here. In this case, it was JD Edwards. So this is kind of another, let's say, the most important second step. First of all, we sit with the stakeholders, do the discovery, and secondly, you map it, how this whole thing is running there. And then it comes to the prototype. And now, once we have understood, yeah, we have this problem here, and now we need to make sure that we, first of all, we understand that. That's another learning we will see at the end of this talk today, that learning and understanding the customer and the product is absolutely the most important thing you can do while making this journey. So once we have understood that, now we are in a position and also have this trust, which is very important, to develop the trust with the customer, that we can now say, okay, here is our prototype that we would propose to address this problem, right? And this problem in this case, as I mentioned, the downtime tagging is, so we can say, okay, we have to now go deeper and we have to read and, monitor real-time line event data that's coming. You absolutely have to do that. So now you can see, we are gradually entering into the kind of data-driven models and also, the whole digitalization space. And you have to also, this is the moment where you would see that there is kind of vintage machinery there, some things that are not even connected to the backend systems, or there is no sensors. So you have to also propose, this is exactly the time where you would propose, how we would like to retrofit some sensors so you can get data out of it. And again, you would need to find some historian, because that's where the whole data would go. That's where you would like to run your analytics afterwards, or let's say train your machine models. So historian is another very important piece of the story that you have to bring into it. So in this case, we defined a very simple, dashboard for the end customer, almost like an Excel where you could bring in data and kind of start recording. And for the data capture here, so once we understood that, so it's another important element. Once we understood that this is very relevant for the end customer, and this is, for example, affecting some 15 different plants that they have. In this case, like more than 50 plants. Then you need to make a call. This is another one which is very important for the business decision making. Are we going to now propose a solution to address the whole thing? Or are we going to do something like, let's do kind of, limited scope prototype here. It's very easy to lose the full project if at this stage of completely kind of new use case and undefined situation that you can then, for example, go into full deployment. So we said, okay, forget about the full scope here. Can we target one plant? Or maybe 2 or 3 plants. So the customer proposed they would like to do, let's say, 3 plants in this case. So we said, okay, no problem. We can do 3, but we are not going for, let's say, 15 or 20 or 50 plants. So in those 3 plants, we then again identified only 1 plant where we are going to ask them to install sensors. So you see now, it's all about cutting, making only and going only for the most critical of where you want to see the value, right? And so we identified that, and there we then asked to install the sensors, and then we started the data flow. Once the data started flowing, it was very primitive. So please think about it again. Very, very primitive interface. It's not about end product. You will have time to define and polish the product, but this is not the time to spend time on polishing the product or making it like beautiful or anything like this. Is really about proving the value and functionality, the value to the end customer, which is another learning that I'm going to talk about later on. And now you can see here, these are then some of the key elements that we got out of it. So we got real-time process data. We already started tracking OEE, and we got really centralized control rooms where you can see, and also multi-site visibility. So already with this very, very basic prototype, all these outcomes were achieved. And that kind of made us, and in a very trusted situation with the end customer, and we got then the final project. And what we proposed in this case was then 4 modules. So again, another input, going from prototype to product is you have to modularize, you have to think in chunks. Generally, the customers nowadays are absolutely not interested in having a monolithic system. So you cannot say, here's my system, it solves all your problems. It has to be modular. You have to identify what is the lowest hanging fruit, in a kind of quantum manner. Can we address this thing first? Can we have then the second thing? Can we have then the third thing, the fourth thing? So this was our approach here, that we said, let's break this whole problem down into 4 different elements here, and then we will start with the downtime tagging there. And then, long story short, fast forward 2.5 years roughly, this is the final product that's now running at this end customer. So this is how the operator sees their workbench. This is how we implemented, with our technologies, the solution. And then they can go, for example, into this, downtime tagging screen there. They can see live events coming from PLC data or from real-time, machine data. And then the operator can go in the which machine component is having the problem. Is it kind of bagger or belt, or is it like conveyor? And then they can choose what was the first top level cause that it happened. Was it jam, for example? And then if it was jam, then why did the jam happen? The second level. And then you can capture, for example, what happened there, any video, for example, or picture, and then add comments. And then the whole data kind of starts automatically flowing into the backend. As it flows into the backend, it really starts gathering the whole insights and KPIs, and then automatically the data feeds into the business intelligence dashboards. So this is really kind of the journey that I wanted to highlight here. Please do not take it lightly. This is, it's very enriching. It requires a lot of interaction, but there is no shortcut. You can, and it would be absolutely false to start with this kind of a thing, because you cannot. It has to first, prove value, and then you have to gradually take steps to this one. And I just brought some other example, but in a similar way, we ended up, creating the second product, which is about preventive maintenance, where you can, look into the shifts and, the production lines and gather data. And then you can have, plant scores and run the intelligence behind the scenes. And then you can, propose or actually evaluate, how the efficiency is happening. And actually the third one, where you can have, for example, the CMMS and how, for example, the work orders are happening. And then really installing kind of big screens there so the customer can see the data. These were all whiteboards, papers where people were writing, in a very modern company otherwise. But that's where the value of digital operation and the digitalization is. Immense value to be created if we can, find a way, first of all, to have nice prototype and then really move from there into a nice product. And what are the learnings, some of the top level learnings? First of all, you have to pivot. We identified in the beginning that the immediate crashes or the lack of data wasn't an important thing. You have to look, for example, can we go into the downtime, for example, and can we tag that data? So that was immediate pivoting. You have to keep pivoting. The POC has to be very well defined, but not really kind of, too much or too expanded in the beginning. And then you need to find incremental expansions there, right? And most important, if there is any one single thing that you can take away from this call today, that's consultative selling, consultative solution approach. You have to be consultative. Please do not dictate or tell you this is how it's going to be. This is my platform. It's very good. This my product will solve your problem. No, that's not the way the digital operations and the AI works. It has to go through consultative approach. Consult them, and gradually coach them and then bring them into final product. And understand the value of the ROI that it brings when you are making a prototype into a product. Without this, you will not succeed. And here are some of the top level ones. I'll not go into each ROI, but this is an example for you. This is how it should look like, that how is the supervisor productivity going to be improved? What is the company goal on top level? What is the machine operator going to get out of it? Everything. Without this, it will stay just a prototype. With the ROI, it is then seen as a product. That important step has to happen. And you have to sit with the customers to kind of, compute it and work together on getting this done. Without this, there is almost never a production order that you will get or a purchase order there. So this was kind of the top level and main important thing that I want to bring, but I did bring also some, quick things for you to, to share with you. For example, positioning AI is very important. There are like 4 levels that you have to go through there. Really, first of all, understanding the descriptive level, and then going to diagnostics, why it happened, for example, to predictive, is it going to happen, likely going to happen or not? And then prescriptive, really telling, for example, how it is happening, and why, and can you change something to do something different about it? And this is where also, Dr. Ranjan is working, and really their company is also bringing a lot of inputs there where they can prescribe almost, how the things should change so you can get a desired outcome there. You have to keep these different stages in mind. Please do not start anywhere. You have to know, can we start with the bottom one and then gradually kind of increase to the next level. And then finally, another thing also worth mentioning is in many cases, you would see that most organizations think that they have all the data available and now they can go towards predictive and prescriptive. Wrong. This is not the case. In many cases, you would like to then move here and you would immediately say, no, you're missing this, you're missing that. And there then you would see, hoops happening, kind of, you go back, for example, and then you have to start sometime for missing sensors, missing data, get them connected and then integrated and then come back. So please keep in mind that in many cases, you have to start from beginning, even though the customer is thinking that they are already there. Many times the data required for prescription or prediction is missing there. And finally, some of the, I would say, really kind of distilled knowledge that I would like to share is, please understand the product, learn extensively about it, always define outcomes and ROI, KPIs. Without this, there is no final product. It will just stay prototype. Focus on infrastructure. Can you scale your infrastructure rather than focusing too much on the final solution? You have to do incremental rollouts. Do not wait till 2-year deployment time. You should deploy soon, but simple, and then keep on increasing. Think about that you would have to need to retrain AI. How are you going to do that? This is very important. That's often forgotten from prototype to product. And really, there is no access to reality and to kind of product without having stakeholders on board. It's all about adoption. Really, that's what it is about. So that's all from my side. Thank you so much. I would like to see if there are any questions. Let's stay connected. Here are my social accounts. This discussion shouldn't stop here.
Dr. Rasif Rana, thank you so much for giving a vivid, real example of prototyping to productization. This is a process where many teams fall apart. Converting an idea to prototype and then to a product is a challenge.
Absolutely.
The streamlined example provided by you, it gives us a very valuable guidance. Thank you so much for your time today, Dr. Rana. We actually had few questions, but I think you already have provided answers in your session. So I think we can move ahead. Thank you so much for joining us today, Dr. Rasif, and for your time today. Thank you.
Absolutely. Thank you, everyone. Thank you for having me. Thank you.
Okay, we now move forward to our next session for the day. This is Computer Vision and Deep Learning, session 1 by Dr. Shubhajit. We welcome Dr. Shubhajit for this session.
Hi, I first want to make sure that I'm audible and I'm visible. Okay. Hi, Bharti, can you hear me and can you see me?
Yes, yes, you're audible and you're visible.
Great, sounds good. Thank you so much for inviting me, and I'm super excited for this session today. This will be the first session on computer vision and deep learning. We will travel a long journey. I'll go slow. Please feel free to interrupt me anytime you think you have a question or there's something that you cannot see in this slide or in the board over here. With that, let me start my screen share first. Can you see anything yet?
We do not see your screen, Dr. Shubhajit.
Okay, so let me try again. Okay, how about now?
Yes, now we can see the screen.
Okay, great. So let me start. So today is the first day for computer vision and deep learning. And in this session, I will go from the fundamentals to the more complicated concepts that you need to model image data. But before we go ahead on the how and what of computer vision, I wanted to first talk a little bit about why do we need to learn computer vision? Why is it important? And I want to show you some of the applications and use cases which makes it very relevant in today's world. For example, this case, which is pose estimation, essentially what it's doing is that an AI system is looking at the video and is automatically understanding the pose of the object here being the person who is exercising or training for Taekwondo. So there are a lot of applications for this kind of technology. For example, in games, you may use this technique to detect your enemy's posture. And based on that, you can make decision. You can also use these kind of AI systems for safety purposes. For example, in a crowded setting in a public space, you can see how people are falling down in a certain area. Let's say there's a slippery slope over there, or maybe a step that is often is hidden. People often miss to see that. So you can detect all of that from the CCTV camera footage and make improvisation on top of that. So this model that Google open source is called MoveNet, that you can download from this link and directly use it and see how fast and how precise the results from this model is. And this is pre-trained. You do not even have to train the model. You can readily use it for your application. There's other applications of computer vision as well. For example, in COVID pandemic, from camera footage, you can directly see and detect how many people are actually wearing masks and what is the distance between people as they move around in a public setting. So there is very good application in the sense that are people following common guidelines that are provided for public safety. Similar application of this technology has also been in places like shopping malls or in retail spaces where companies want to know which areas of a shopping mall people visit more, or when they're looking for items, which aisle or which shopping shelf are they looking at. So they track the gaze of the person. Based on that, they improvise upon the way they have shelved their retail spaces. And they also provide better traffic layouts so that there's less collision between customers, and then they can easily find the items that they're looking for. There are other applications as well, such as this cancer cell detection, where conventionally pathologists look at thousands and thousands of images of brain scans. And these images are at different magnification level, 1x, 10x, 20x, 30x, and 40x, and so forth. So for each pathologist, they have to look over thousands and thousands of images and come to a conclusion if that cell has cancer or not. And there are multiple pathologists looking at the same image, and the consensus between these pathologists are really low, like 48% or even lower than that. So because it's a very tedious and a very difficult task. So there's been a lot of work in AI where automatically these models are looking over these images and automatically predicting if this cell that they're looking at has a tendency or a likelihood of being cancerous in the future or not. So from the model that they have presented here by Google, the accuracy is over 89%. So that is phenomenal. So you can imagine that how much this can help physicians and pathologists in deciding on whether a certain patient is diagnosed to be cancerous or not. So this is another example which I and Dr. Chita in one of the sessions early on talked about, where we talked about how AI can be used to reduce waste. So in this work, in the table that you see, in the columns, these are different materials like glass, metal, paper, plastic, and trash. And these are the different images that are collected. And each row represents the different computer vision models, and it shows the heat map, it shows what the model has learned. And based on their learning, they're predicting them of a certain class of garbage. For example, if it's a glass, if it's a metal, or is it a paper. Based on that, this model can help humans to categorize the garbage in different categories. And using that, we can reduce wastage by a certain percentage. So this work is also extremely relevant. And all of this requires fundamental knowledge of computer vision and algorithms that uses image as a source of data. So if you see over here, this is the basic pipeline. You first use image data and you process it. So you have an original image, and that image might not be in a shape which is useful to train your model or to learn anything from it. So you may have to process the image in various ways. One of the processing techniques is to augment the image by randomly scaling in different ways, or flipping its orientation horizontally or vertically, or translating it. And by augmenting the image, you're basically improving your training data so that your model gets to see a more diverse set of input images, so that any image that you show in future, it can successfully predict what class label that image belongs to, or what are the objects that image contains. So today in this session, I will talk about image processing, how you can process image. And in that image processing pipeline, I'll specifically talk about how you can augment your data. Here, data meaning image data, how you can augment your image data to improve upon your training set. In the tomorrow's session, I'll talk about convolutional neural networks, CNN, which Dr. Chitta has already talked about a little bit in the previous session. I will extend that conversation further and show you how you can use very primitive image processing techniques, data augmentation techniques, to build a very robust CNN model to perform very simple image computer vision tasks, such as image classification or object detection. So for today, this is our outline. So I'll go with image data fundamentals, meaning what is an image data for us and for computers. Then I will show how you can process and manipulate an image data using libraries such as Opencv, Pillow, and others. Then the rest of the session will talk about machine learning tasks that you can follow on these images that you process and augment. I'll specifically talk about Tensorflow, which is a very robust deep learning library and very useful for image data processing, and also for modeling CNN and other deep learning models with images and other sorts of data such as text or even audio and so forth. So let's start. So in the first section, I'll talk about image data. So usually, image processing workflow contains, you first get images, you read them in your computer, perform a set of low or high level image processing tasks, some examples being cropping images or rotating or flipping them or changing the color and so forth. Then you probably want to save it as a new image for your other downstream tasks, or you can visualize it to make decisions based on features that you have learned or features that you think the system can learn for other downstream tasks. So this is the basic pipeline. You bring in images, you process them, then you write or visualize. But first I want to ask, what are images? So we see images all the time. We go out for a walk, we take images. We are on social media, we see images that others post. So for us, images are these beautiful colored blocks with a lot of objects and a lot of information. We usually save them as JPEGs or PNGs or SVGs. But are they the same thing for a computer? So just to give an example how a computer sees an image, let's say this is a very simple image of basic shapes. The black outlines represents the shape that you see. So we as humans can easily understand there's a square, there's a rectangle, there's a triangle, this is an ellipse, and so forth. But how a computer sees this is something like this, a matrix of numbers. Here, the dark pixels are represented by ones that you see over here, and the rest of the image, which is white mostly, is represented by 0. And this is, I have simplified it, but this is how images are represented on a higher level. You can also go into this link and see how any of your image that you're interested in, a computer sees in this sense as divided into 0 or 1 or some integer values that you can specify. That will give you an understanding of what images means for us and what images means to a computer system. So usually there are two kinds of images, 8-bit and 16-bit. So for 16-bit, 8-bit image, you can store for each pixel values, integers between 0 to 255. For 16-bit image, you can store values from 0 to 65,535. You can also go into this link and play around with the pixel values to see how the colors change per pixel. So this is an example of a matrix filled with numbers, and each cell over here represents a pixel, and the pixel can take value from 0 to 255. If you have values closer to 0, you will have darker colors, more close to black. And if you have values closer to 255, you will have values more close to white. So images often contain multiple channels. A very popular image format that we are aware of is RGB, red, green, and blue. And these are usually stored as separate matrices. So you can see that this is one matrix. Let's say this is for red, this is for green, and this is for blue. So this is usually stored as 3D volumes, each layer meaning each matrix. So you have 3 matrices to represent an image over here. So now that we know how images are stored in a computer, not just how we store them as JPEGs or PNGs, but how a computer sees them, let's move on and see what are the different image processing tasks we can do with this data set. So first, I want to specify how images are coordinated. So spatially, images are read from the top left. So this corner is 0, 0. And you begin your indexing from the top left to the right and to the bottom. So at the extreme right, this is 7, 7 because 7 pixel width and 7 pixel height is what you're looking at now. And in Python, the indexing starts at 0. So that's why I have pointed the first column and the first row as 0. So each dot here, like I said, or each square is a pixel, and more pixels means there is more accuracy. So now that we know that images are stored as 3D matrices, here each matrix is filled with numbers, integers, and they represent different channels. There are different data structures out there in Python to store such information. The default data structure called lists is good enough because you can store these matrices as a list of lists. But there's also the library NumPy, which has ND arrays as the data structure that is often used to store images. And then there's TensorFlow, which has a concept of tensors, which helps you store the data as ND arrays, but also helps you perform other computation which is relevant for neural networks, such as gradient computation or back propagation and so forth. So I'll go over these in a bit in the coming slides. So there are various libraries in Python which helps you process images. A few of them being Pillow is a very popular one. Opencv is even more robust than Pillow and more popular. There are some others such as Skyimage and SciPy. They also have a lot of functionalities which helps you perform image processing. So I'll begin a bit with the Pillow library. Whose documentation you can read over here, which shows how you can install it and how what are the different functions out there. So let me click on that and see if I can open it. Yeah. Do you still see the web page that I have opened?
Yes, Dr. Shubha, this is visible.
Okay, great. So in here, you can look at all the different ways you can process images. For example, you can read and write images. You can cut, copy, paste. For example, you can crop a section of the image and then paste it on top of another image. So these are basic building blocks of image processing. But let's say you have a batch of images, let's say 1,000 images, and you want to process all of them with similar logic. You can write a function and run the whole batch at one go. Usually in graphical user interface based programs such as Photoshop, you can do the same thing but more with menus and widgets and so forth. For example, here, I can crop a section of it, I can copy, and then I can paste. So you can do all of that using Python's libraries, and you can do for a large set of objects.
Oh, sorry to interrupt, Dr. Shubha. Your screen is not visible.
Oh,
the
okay.
Photoshop screen, that is not visible.
Okay, so you cannot see my Photoshop. So let me share my screen. Can you see now?
Oh, yes.
Okay, yeah. So what I just showed is that you can open an image, you can crop or take a section of it, and you can paste it back. So all of that is possible in Photoshop, but you can also do those with image processing libraries. So I'm going back to my PowerPoint. Let me know if you see anything. Do you still see my PowerPoint?
We can still see the Photoshop window, the monkey picture.
There's some issue with Zoom's sharing of the whole window. So instead of that, it's showing partial screens. So, okay, now can you see?
Yes, your PPT is
Okay.
visible now.
Okay, great. So yeah, so just like I said, in Pillow, you can use all these techniques like cropping, rotation, scaling, adding noise to add some kind of blurring to the image, changing the color space from RGB to CMYK. And to be clear, in RGB, you will have 3 channels. In CMYK, you will have 4 channels. So images may have multiple channels. It will be 3, 4, or maybe more if it is a different color space. In grayscale, you will have only 1 channel because it's only between black and white. There's no other color information there. So I'll stop a little bit here for some questions before I move on to the next stage. If there is no question, then I can keep going.
Yes, Dr. Shubhajit, I have 2 questions. One is, if you can explain on channels one more time with respect to programming concept. And the second is why we don't want to use Photoshop. Why are we doing cropping and other image manipulation on Python?
Yeah, sure. So for answering the first question, so channels are essentially color information that are preserved in separate matrices. So for example, here, let's say you have an image with 640 and 480 pixel. You will have all the color information pertaining to the red color will be stored in one matrix. All the color information pertaining to green will be in another matrix, and so forth for B, which is black. So essentially what it means is that you're separating your information in these 3 channels, and you combine them together to get all the information from image. So different color spaces have different channels. For example, in CMYK, there are 4 channels. It starts with cyan, magenta, and I forgot what Y and K meant, but essentially there are different ways to represent the color information. To answer the second question, we need Python to do image processing because we are not processing 1 or 2 images. We may want to process a large batch of images. So we may want to have a programmatic way to specify the same set of operations performed on a large number of image, and these images may be a training set to train your AI model. Similarly, we may want to randomize the set of operation that we want to do. Let's say I have 1,000 images and I want to have rotation on them, but the degree of rotation may vary from image to image based on certain characteristics. So maybe some image should be rotated 20 degrees, some other may be rotated 30, some other may be 45. All of that is very easy to do when you're programmatically specifying your operation, rather than opening each image one by one in Photoshop and then performing image processing. Does that answer your question, Dr. Chita?
Yes, Dr. Shubhajit, you have answered this wonderfully. Thank you so much for answering this question.
Great.
For now, we do not have any more questions. We can move ahead.
Sure. So let me go to the next part of the talk, where I will be talking about Opencv for image processing. So Opencv is a bit more advanced in terms of functionalities it provides. It has over 2,500 optimized algorithms, and optimized meaning that they have written the code in a low-level language such as C and C++ to ensure that the operations and functions that you're calling is fast, so that your batch processing on a large set of images are fairly quick. They also have more complex algorithms and functionalities in comparison to Pillow. For example, you can detect objects in an image. For example, here in this image, this model written in Opencv can detect there are 2 objects. One is a dog and one is a cat, and the number here shows what is the accuracy percentage, like how confident the model is that this is a dog. So it's 98% confident. It can also generate 3D point clouds based on an image of an indoor space or even outdoor space. And all of those things are extremely relevant for people working in computer graphics industry or even in building design industry. So in the next few slides, I'll talk about some of the functionalities, and also in a notebook, I will show how you can use these Opencv to call different functions that of image processing that I will talk about. So one of the ways to represent an image is image histograms. So here that you see is an image, and on the right, it shows the distribution of various pixel intensities. So you see on the x-axis, it is distributed from 0 to 255, and it shows which pixel intensities are more frequent than others. So this is one of the ways how images are analyzed and further processed to redistribute the color information, because an image may be dark on certain sections, so you may want to increase the contrast on that section without losing too much information in some other sections. So what I just said, it just writes over here as well. So you can determine how the quality of an image based on looking at the histogram, and you can also see the same in Photoshop. So in Opencv, there is a function called Equalize Hist, which essentially automatically equalizes the histogram information. For example, before calling the function, the pixel probably was mostly distributed on the center, and these on the left and right were the low intensity areas. But after calling the function, it automatically redistributes it so that you have more even distribution of pixel intensity. And the updated image that you see is over here. So you can see in this image that on the left, a lot of information about the grass on the back is smudgy and blurry. But on the right, you will have some details. And there's a lot of room here to interactively change the parameters in this function to see what is the right setting that helps you understand the features in the image, but more importantly, helps the system or the computer or the AI model understand what the features in this image. So moving on, you can also do locally adaptive histogram equalization, meaning that different part of the image can be broken down into a set of grids, and each of these can have different histogram equalization functions applied. For example, here in this image that you see, in the center, the intensity of white is pretty high compared to others. So the equalization effect that you apply here should not be applied to other areas because that will not work well for the image. So in that setting, you may have different functionalities added, different histogram equalization added to different parts of the image. And then you can merge all of this together to formulate your final image. So the next set of image processing functions that you can apply is at the level of a pixel. So essentially, these are also called point operator. So here what happens is that the output of a pixel value depends on the corresponding input of the pixel. So whatever the pixel value is, let's say 78, I can apply a function on it, let's say a linear function, multiply with a scalar value, and the output will be a scaled update to that pixel. So this kind of operation is used to change the brightness and contrast, or you can change the color, or histogram equalization is also an example of point operator. I would highly recommend this book if you want to know more about how point-based operations can be applied to different pixels and what kind of results you can get, and other computer vision algorithms such as object detection or image segmentation. This book is my go-to book to understand the fundamentals. So moving on, so for point operators can be applied to each of the channel, or it could be applied to only a single channel. It depends upon how you have designed your image processing task. So for example, this is an this is how a pixel gets updated. So let's say your original pixel was represented by this function f I comma j, meaning the cell coordinate, and you apply an operator p on it, and your updated function would be updated pixel would be g I comma j. You can also have a different linear function, and this is how your point operator works. So this brings me to the space of image filters, which are also sometimes called neighborhood filters. Essentially, what happens is that you have an input image, which is represented by this matrix, and you bring in another filter or a kernel, which is a smaller matrix with a bunch of numbers, and these could be any number. This could be floating point values or integer values, and essentially for each pixel you do additive, you do multiplication for each pixel, and then you sum them, and the result gets replaced to that pixel value. I will show this in a whiteboard in a bit, but this is a fundamental concept in image processing and computer vision, and all the models, specifically the CNN models, are based upon this fundamental aspect of how you can apply a filter to an image to extract relevant information, such as you can sharpen the image to find the edges, or you can blur a certain section of the image to highlight some other section of the image, so forth. So let me now stop sharing my screen and draw it out to show how this operation is performed. So I'm drawing here in my board. Let me know if you can see what I'm drawing. Is it visible? I just draw a square.
It is visible, Dr. Shiva, but if we can use a darker one, yes. Yes, this is better.
Okay, so let's say this is one of the channels of your image. And for simplicity, I will just add in 1 and 0, but these could be values between 0 to 255. So let's say you have 1 pixel 1, then 0, 1, 1, 0, 0, 1, 0, 0, 1, 1, 1, 0. So I'm just randomly filling it. I'm imagining there's some image which has this distribution of pixel intensity. Okay. Now I have another filter, which is, let's say, a 3x3 filter, 3 columns and 3 rows. And let's say that filter also has 1 or 0. This can have any number like 0.1, 0.5, 0.6. You can also have another linear operation, let's say divide by 1 by 9 or something like that. You can also increase the size of this filter, but it should never be more than the size of the image. It should always be lesser than that. So let's now go with a simple filter. So how this operation works is that I will superimpose this filter for each pixel. Let's say I'm just trying to calculate this pixel. So I'll superimpose this here. So when I superimpose, what will I see? I will have 1 here. I will have 0. I will have 1. Then I will have 0. Then I have 0, then 0, then 1, and 1, and 1. Okay. So now that I have all of that information, what I'll do is that to calculate the updated pixel value of this location, I'll multiply each of them and then sum them. So what should I have here? So it should be 1 multiplied by 1 plus 0 multiplied by 0 plus 1 multiplied by 1. So this was the first row. Then 0 multiplied by 0, then 0 multiplied by 0, then 1 multiplied by 0. Then the last one has 1 multiplied by 1 plus 1 multiplied by 1 plus 1 multiplied by 1. So what should I get here now? So I'll have 1 plus 1, 2 in the first. Second will have all 0. And third will have all 1. So 1 plus 1 plus 1. So I'll have 5. So in the new image, the first pixel will be 5 now. Okay. So to calculate the next pixel, what I'll do is I'll move this filter 1 step here. So now the new position of the filter will be here, and then I will calculate the values and update it over here. Okay. So any questions for this? I'll pause a bit if you have any confusion, because this is fundamental, and once you know it, everything else will be pretty straightforward.
So, Dr. Shubhajit, what you showed here is basically to detect an object in the image. So similar to what, not similar to, so in continuation to what we were learning yesterday, that we sweep an image with a filter, and when there's a match, it detects. So when there's a match, the value of this will be very high. So can you elaborate on how this converts into finding an object in the image?
Yeah, sure. So those two concepts are related, but here we are not detecting any object with this. We are detecting features in the image. And these numbers in the filters. In a neural network, these numbers are randomly initialized, and we train the image, and it learns through the process, and it starts to map the number with the label that image is in, or the object that that image contains. But for today's, some of the examples that I will show, there are some filters that are already designed and researched out, which are very good to detect and extract features from an image. For example, extracting edge information or blurring out certain part of the image. Or another is, let's say, the median filter, which blurs the image, but at the same time preserves the edges of the image and so forth. So the big idea is that using this filter and sliding it through the image, we are able to take the neighborhood pixels information and update that particular pixels information with its neighbor. And using that knowledge, we are trying to learn if there is any distinct feature that is useful for us. So let's say if we have an image, let's say we have a mountain. So all of this is dark and the sky is light. So that means in this line over here, there is some spatial change in terms of color intensity. So when we do perform this kind of neighborhood filtering, so it takes into account the neighborhood region of that line. And if there is any difference, that will get recorded and you will get to see that feature more distinctly. Does that clarify the question, Dr. Chitra?
Yes, yes. Thank you, Shubhajit. So basically, these filters are helping me find those patterns. I cover the entire image to find those patterns in it.
Yes, yes.
Thank you.
Okay. So if there is no question, I will move on to my presentation. Yeah. You can see my slide, right? Can you see my slide?
Yes, it's visible.
It's visible.
Okay, great. So what I just said is essentially this operation is also called convolution. It helps you find features in the image, such as you can blur or sharp, or you can extract edges and so forth. There are various examples of such operators. And like I said, in neural networks, you randomly initialize these numbers, but researchers over the years have found some presetted numbers, which are extremely useful to detect features, such as the Sobel operator. It has two variants, horizontal and vertical. And you can see there's a very distinct 0, 0, 0 vertically, which helps you detect horizontal edges. And there is a distinct 0, 0, 0 horizontally, which helps you detect vertical. And you can also combine these two to create the Sobel filter. So, and again, you do not have to do any of that manually. Opencv has functionalities which does this for you. But it is extremely critical to know the fundamental, because you may want to be creative and design your own filter and come up with new ways to process and modify your image. One distinction that I want to clarify is in deep learning, we use it on a convolution, but in pure mathematics, this called the same operation cross-correlation. It's just its way the images are stored and specified. So in cross-correlation, you just have to flip the kernel relative to the image, and then you perform the operation. But overall, the big concept is still the same. Flipping the kernel means, like I just showed you, the small filter matrix. You can just flip it and then perform the multiplication and addition operation. So there's also other filters, and all of these are linear filters, meaning that they are commutative and associative. So performing one filter after another would be the same if you reverse or if you change the order of applying the filter. So they are linear in that nature. So for example, box filter is one of the examples where you blur the image. So and again, box filter have a different set of numbers, which we will see in the filter matrix. Then Sobel operator, which I just described, when applied to this image, will show you distinctively the edges that define this image. And this is something that may be very clear for us as humans, but for a system, it may not be clear. It may be blurred with all the other numbers that are out there. But after adding this operator, other numbers are dimmed down and only these edges, those numbers are pushed up so that the computer can easily understand what defines this image. Okay, this is the example of box filter that I just talked about in the previous slide. You will have a 3x3 filter with all values being 1, and you divide that with 1/9. And in Opencv, you can call this function cv.blur or cv.boxFilter to apply this to any image. Okay. So those were all linear filters. There are also non-linear filters. So in non-linear filters, such as median filters, minimum and maximum, you do not have to multiply a filter with the image. What you do is that find the minimum value from the neighborhood space. So let's say if I have to find the minimum value from this 3x3 box here, let me draw it with a pen. Yeah. So in this, the minimum value is 1, so this will be replaced by 1. So here I'm not multiplying by anything, but I'm just looking at the neighborhood space of this pixel and finding the minimum value. So that will be a minimum filter. The same would be for maximum. So here I will just find the maximum value and replace the 1 with the maximum value. Then there is median filter, which essentially I will sort all the numbers that are in the vicinity and find the middle value and replace the 1 with that middle value. So these are minimum filters. These are minimum, maximum, and median filters, which are examples of non-linear filters. Then there's Gaussian filter, which goes with the Gaussian function. And this whole matrix is essentially what a Gaussian filter looks like. I'll not go into too much detail of any of these, but it's essential to remember that all of these are neighborhood filters, and neighborhood filters are of two kinds, linear and non-linear. These are non-linear, and the ones that I described earlier, like box filters, Sobel filters, and others, those are examples of linear filters. So there's a bit of a homework for you. Read documentation in Opencv and find out a bit more about bilateral filters and iterative adaptive filters such as smoothing and anisotropic diffusion of an image and other functionalities. You may also want to know distance transforms using distance functions such as Manhattan distance, Euclidean distance, or cosine function. These are some work for you, and you can come up tomorrow with questions if you have some a problem understanding what they are. Okay, so to summarize, we learned a single pixel operation, which is changing the color of a pixel by a linear function, or changing the histogram by transforming the way the pixel intensities are distributed. We learned neighborhood operations, which are also called convolutions, and there were two kinds, linear and nonlinear filters. And there were some geometric transformations like scaling, rotation, and translation and shear. In the next few minutes, I'll go into my notebook and show you some of these operations done in Pillow and Opencv so that you understand how these functions are called using these libraries, but also what is the output that you expect to see when you call these functions. So let me share my notebook to show what I mean. Do you see a notebook open in a browser?
Yes, Dr. Shubha, this is visible.
Great. So I have shared this as a PDF to you. You can go through that in more detail. In this notebook, I have called Opencv, Skimage, Pillow, and Matplotlib to do perform various image processing and manipulation tasks. You can use any of the locally saved images that you have in your computer. But I have used open source images from these links specified in this list. You can also do the same and play around with various images that you see online and see how you can process and manipulate them. So in the first cell here, I'm reading an image using the SK image library. And like I said, an image is represented with matrices, so the list of lists. So you can see these are all the numbers of pixel values. And with these square brackets, you can understand they are list of lists. Yeah. You can also call the D type to understand what data type they store. So in this, they are storing integer. This is the dimension of the image. You can call it the image.shape, and you get to see width and height and the number of channels it has. So right now, they have 3 channels. You can perform that same task using Pillow. So I'm using image.open functionality from Pillow to open another image. And in Pillow, when I directly type in the output of this, it draws out the image instead of showing me the numbers that this image represents. So this is an image of a monkey. I can also look into other metadata, such as format of the image. If it was stored as JPEG, I can look at the size of the image. So it had this many pixels. And I can also see the color space that it had RGB. It was an RGB color space. I can resize the image just like I would do in Photoshop in any other program. So for example, from 1752 by 1160, I resize it to 600 by 480. Then I can also crop this image. So like I said, an image starts from 0, 0 from the top left, and then you go to the right and to the bottom, and you increment the dimensioning. So here, if I'm cropping it from 75, 200, that means I'm going 75 in the X direction, 200 in the Y direction, and then I'm specifying this height width, 200, 250. And this is what I get out. This is something over here. Now what I do is that I transpose it, meaning that I rotate this cropped part of the image. Then I paste it in the original image, but in the same location. So you see, I provide the same XY coordinates and the same size, width, and height. And this is the output that I get. So the resized image now has the original image, but the cropped part is pasted on top of it. Then there's other operations. For example, I can resize the image first by cropping part of it. So I just cropped this much. Then I pasted the cropped image on the original image. So now you have 2 image parts that you're looking from, taken from the same image. So it's kind of a collage work. So this is where this task has 2 downstream tasks. So one is if you can be creative, you can create, programmatically create interesting images, which is fun to look at, or something that an artist only can imagine. The second is you can, for a machine learning task, add more variation to your data, because real world images are not clean, they're not smooth, they have a lot of occlusion, a lot of ambient noise, and so forth. So you can process your input training set and add noise by doing all these operations. Similarly here, using Pillow, I took out all the channels, and then I converted the RGB space into BGR space. So I changed it. So now you see the color spaces are different. So now the same image have blue regions showing, which was before more on the orange and reddish zone. You can also perform rotation, like now I rotated it by 45 degrees, or you can have a sequence of operation applied to it. So rest of the notebook is fairly self-explanatory, and you can go over it and understand what are the different functions you can apply and process your image and update it. You can also write your updated image in your local disk. In this case, I'm running it on Google Cloud, Google Colab, so it will be saved in my cloud, or if it is connected to my drive, it will be saved in my Google Drive. The same operations you can do with Opencv. So here I'm reading another image of this house in Opencv, and by default, in Opencv, the color space is, I think it's BGR. So you have to transfer from BGR to RGB, because when Opencv was written, BGR was the format that was used in various applications. But now we mostly use RGB. So that's why if you want to see the true color space of that, of this image, when you transition into RGB, it looks like this: blue sky and a yellow light within it. You can also make collages of different images. Like I talked about, you can visualize the histogram of the pixel intensity. You can also visualize different channels pixel intensity between the range of 0 to 255. You can see which part of the R or green or blue has higher pixel intensity. You can grayscale an image, then you can find contours. You can also apply very simple linear transformations like subtract a number, integer number from a gray image, or you can add subtract an image from another image, and you will see very fun results. You can also add a noise. For example, here I'm adding this noise to the image, and this is how it looks like. This reminds me of the smog situations happening in different places of the world, like in Delhi now. So let's say you have an AI system which is trained on very clean images, but you deploy in a location where there's pollution or some other local noises, and your AI system will not work well because it hasn't seen such images. So you may want to retrain your model based on augmented images or processed images based on the locally available real world images out there. So that's the whole point of learning how image processing works and how you can programmatically perform all these tasks without having to rely on a graphical user interface kind of program like Photoshop. So in the interest of time, I will move ahead and go back to my slide. Let me open that. In the meanwhile, I will request if you have any questions, I'm happy to answer before I move on to the next section.
We do have a couple of questions, Dr. Shubhajit, but we can take them after your session. Rather, can we take a 2 minutes break?
Yes, that's what I was going for. So let's reconvene in, do you want 2 or 5? I'm okay with anything.
We can take a 5 minutes break.
Okay, sure. I will be online, but muted and video turned off. So as soon as we are ready, just give me a heads up.
Sure. Thank you, Dr. Shubha.
Yeah.
St. Claret College, situated in North Bangalore of Karnataka state in India, aims to create an informative and sensitive future citizens through Claretian mission of education.
At St. Claret College, the focus of our education is to form individuals of character and integrity. Individuals who would become agents of social change and transformation. And for that to happen, we will certainly provide our students well-rounded education.
Situated on a serene and picturesque campus in the Garden City, Bangalore, we provide world-class state-of-art infrastructure and facilities to our students.
Our graduates become critical thinkers. Our graduate becomes individuals who are really very creative. And that happens when we provide them with an engaging curriculum. A curriculum that certainly responds to the needs of the industry, responding to the needs of the times.
Claret Group of institutions caters to a large number of students, more than 9,000 in its campus, enabling them to understand and learn together to become thought leaders.
We believe in education that is inclusive and socially just. So Claret College has been offering education at an affordable cost to help and support everyone's aspirations.
Holistic growth of students is the core of our educational mission.
The education that we offer is faith-based Catholic education. And at the same time, we know the term Catholic literally means universal. And our education is inclusive. Our classrooms certainly represent the diversity of culture, diversity of languages, diversity of belief systems that India represents. And we offer our students the best so that they become global citizens.
Welcome to Claret College, the abode of knowledge.
Dr. Shubha, we can resume now.
Okay, great. Let me open up my slide. You can see my slide.
Yes, Dr. Shubhajit, it's visible.
Great. So the next part of the talk will be on, now that we know we have image data, now that we know how computers read image data and how we can process them, the next part is how can machine learning be applied to image data? What are the different tasks we can do, and what are the downstream applications of that? So there are various wide range of tasks that we can do using image data and machine learning. So one of the most common ones is image classification, which means that you have a large set of images and which are already pre-specified in different categories, such as this one. This is an image of a monkey, and the category here is monkey. So you have image and a label, and you want to train a machine learning model to automatically categorize so that in future, if you have a new image and it show it to the machine learning model, it will automatically predict the label of that image. So this is one of the most common machine learning tasks on image data. Then there is object detection, which is essentially not only finding the category or the label of that image, but also finding objects that resides in that image. For example, here we have a dog and a cat, and we also have object localization, meaning we are locating the location of the object in that image. So we are also showing these bounding boxes, which represents where they are. This is a bit more complex task than image classification. The nature of annotation is a little bit more different, but this also have more different kinds of applications. Some of the ones that I already talked about early on in the presentation, such as detecting people from a live video stream if they wore masks or not. Then there's a new class of models called GAN models, which are able to generate new images based on a distribution of images that they have already seen. There is a website called thisfaceisnotreal.com or something like that, where such kind of models have generated people's faces, and they look so real, you will not even understand that's not a real person. So for today and for tomorrow, for today especially, we'll focus on image classification. Tomorrow, we'll go a little bit more in depth of image classification, and then also talk a little bit on object detection. So like I said, in image classification, our goal is given an input image, train a model so that it automatically predicts the label or category, as a dog, as a monkey, or a cat. So what we expect out from such an system is the classification results, like the label, and also the likelihood of the confidence, like how confident you're this is a monkey, or how confident you're this is a dog, or how confident you're this is a cat. For example, in this case, let's say if I'm predicting, I'm inputting this image, it may give like 65% chance that this is a monkey in comparison to others. So how do we train a machine learning model which can classify images? So there's a big pipeline, which we talked about a little bit in the earlier sessions. This pipeline can be broken down into three separate sections: data processing, modeling, and deployment. Today, we mostly learned about data processing, like how should I specify my data so that a model that I want to train can ingest it and perform the task that I want it to do. So the first part is prepare your data set. And in that, a very important step is to split it in separate sections: training, validation, and test. And I will talk about it in a bit. And the next part is design and train a model. So there are different machine learning models are out there for different data types: text data, image data, tabular data. So there's a wide range of modeling choices that you may want to make. So this is the part where you design your model. What class of model you're picking? What are the different hyperparameters or architecture settings? Meaning that if it is a neural network, how many layers? What is the dropout rate? Or what kind of regularization function you're specifying, and others. When you have designed a model, you want to train the model with your data, and you also want to validate the model by showing it unseen images so that it performs well on unseen data, because you do not want to train a model that only predicts the label for the images that it has seen. It has to be useful when it can automatically predict labels for images that it hasn't seen. Once you have designed and trained a model and validated it, then you deploy it. And this whole pipeline keeps repeating itself, because there's never one iteration and you're done. You always have to come back over and over again to the first step. Sometimes your data is not right. Sometimes there is a label imbalance. Let's say you have 1,000 images of animals, and out of those 900 are monkeys and only 100 is dog, and you want it to perform well on predicting dog. It may not do well because it hasn't seen enough dog images. It hasn't learned enough features from images related to dog. So like I said, preparing your data means preparing images and preparing labels for it. And computers sees numbers. So here, if I'm specifying the labels as monkey, dog, and cat, it will be specified as integer values of 0, 1, and 2. So now the concept of splitting data. Why do we need to split data? Because you want to train on a subset of the data that you have, so that the other subset that is left over, you want to test your model on. So usually for smaller data set sizes, such as 30,000 or 50,000, sometimes people split like 75% is training data, 25% is for testing, and 5% is validation this data, which essentially is data that you think will be deployed, or something that is that will be used when you have finished training. For larger data sets, such as 1 million, you can have more data set for your training set. So you can go 90% for training set, 5% for test, and 5% for validation is good enough. You do not want too many data in your test set, because the more in the training set, the more variation it will, the model will see, the better it may perform. But then there is no right and wrong here. This is a design decision that you have to make when you're designing your modeling pipeline. but you want to make sure that your training and test set is of similar nature. What you're training your model on and what you're testing it on is looks same. Real world images of monkeys may not be as crisp and clear like the one that I have been showing you since the beginning of this talk. This is a real world image of a monkey, and you can see how hazy and blurry and noisy this is. It's very difficult even for humans to determine if this is a monkey or not. And that's why you need image processing techniques to process your input data, to add noise, add blurring, add rotation, and other techniques that I've talked about, so that it simulates or mimics the real world data, so that your model better matches what it's going to see when it's deployed in action. So the first part of the talk was data processing. Now I will talk specifically about modeling. So today I will use a simple fully connected neural network, which are also called dense network, to train an image classifier. Tomorrow I will go into more detail into convolutional neural network, where it will use the convolution process, which I already discussed today, to better represent image features and also better scale to a wide number of images, because images are considered like quite dense in relation to other data sets like tabular data and others. So a fully connected neural networks looks something like this, where you have an input layer where you pass in all the features, and then you set a set number of hidden layers. Then you have an output layer, which is the number of labels. Let's say for image classification, for this task, there was 3 labels: dog, monkey, and cat. So this would be 3. If it would be a hand recognition task where you have images of numbers from 0 to 9, the output node will be 10. So neural networks in general have performed well. They automatically extract features. You do not have to manually specify features. You do not have to manually specify filters and other information about the input data. You just pass the data, and the network will learn the features that is relevant to predict the correct label. And it will give you not only the labels, but also prediction probabilities, like we talked about before. So let me share my Colab to show how we can model it in TensorFlow. I'll share the TensorFlow in a bit. Just bear with me. Do you see a notebook?
Yes, Dr. Shubhajit.
Yeah, sure. So here, what I'm using is a TensorFlow library, which is developed by Google, and it's very useful for deep learning modeling. And I'm going to be using the Mnist Data Set, which they already have in their TensorFlow datasets package. And the Mnist Data Set looks something like, I haven't run it. Let me run all of it. So while it runs, let me go to, so the Mnist dataset is publicly available, but you can also download it directly from this TensorFlow datasets library. So it locally downloads it and saves it. There are a few parameters that you have to specify to train a model. For example, batch size, a number of epochs, number of classes based on your data set, number of hidden neurons, the activation function that you want to use. I'll go into these in a bit before I finish the whole notebook. So the first step that you do is you normalize your image. So as we talked, that the image pixel intensities are between 0 to 255. Here we are normalizing. By normalizing mean that we are scaling it between 0 to 1, so that all the images are more or less in the same same size, same scale. Then you specify your batches using the batch size parameter. For this case, I have specified 128, but this can be varied from any number. But larger the batch size, the faster the model may converge, in the sense that faster it may the loss may come down, but also it may overfit the training data. So that these are some of the trade-offs that you may have to think about. So like I said, you have training data and you also have test data, and you also normalize that. And then you design your model over here. So here, what I'm doing is that I'm designing a fully connected neural network. I'm flattening the input image into one long vector. And then I'm passing it to a hidden layer. There's only one, so that's why this is only one. If I want to add another one, I'll just copy this and specify that here. And here, the number of hidden neurons for this layer may be different, or maybe I can specify a different activation function. So that is a design choice that you make while you design your neural network. Finally, you compile your model. And when you compile, you specify the optimizer that you want to use. In this case, we're using Atom optimizer. There are a lot of different optimizers like RMS prop, which uses, I think, moving average to calculate the gradient each step, and others. Then there is stochastic gradient descent as well. You can learn all of that from the documentation, but for the simple use case, I just use Atom. And then in this model.fit function call, I'm training it. And for this case, the number of epochs were 3. So number of epochs means how many times you want to train it, how many times you want to repeat the experiment. And for each epoch, you will see the accuracy may improve a little bit. Yeah, and then finally, you will evaluate it on test data, and test data meaning it hasn't seen the test data yet. And the result object that you get from the evaluation function gives you the loss and the accuracy, which you can plot. This is a very simple example of a dense neural network which can take in images. One key thing to know in dense neural nets when you're using it to read images is you have to flatten the image as one long vector. So just like I said before, you have an image which is a 2D array or a matrix. When you flatten it, so let's say this is 0, 1, 2, 3, 4, that means 5 columns, and here 0, 1, 2, 3, 4, so there's 20. So when you flatten it, all of that will be one long vector. So all of these numbers will go here. So let's say this is 25, this is 6, this is 19, this will be lined here. And all of this information goes into your input layer of your neural net. Let's say it's your hidden layer, and let's say so all of this vector goes here in a dense network. You flatten the image as one long vector, and that goes in, and then it gives you the number of labels you have. Let's say 3 for dog, monkey, and cat. It will give you prediction probabilities. Let's say 0.9, 0.05, and whatever is left, 0.85 or something like that. Any questions? I can pause here a little bit if you have any pressing question that may not wait.
Yes, Dr. Shubha, we are getting some questions from the audiences. So the first question goes like, how will we decide on the size of the filter? This is by Renny Jose.
Yeah, it's a good question. So size of the filter, there is no right or wrong answer here, but the upper limit is the size of the image. Your filter can never be bigger than the size of your image. And if I go back to my screen. So size of a filter is something, first let me know if you see my screen.
Yes, Dr. Shubhajit, it's visible.
Yeah. So here I have specified some of the parameters over here. And I think the size of the filter, which is here, kernel size, can be one of the parameters that you tune for. So for experiments, you can begin small and then go higher, or you can train your model with multiple filters with different sizes. So tomorrow I will go with a large range of neural CNN models like ResNet, AlexNet, VGGNet, GoogleNet, ImageNet, and all of them had different architectural configurations, meaning different kernel sizes, different number of filters. There are pros and cons of each. The higher the size becomes, the more number of parameters you have to learn. So this computationally, it's more expensive. At the same time, your data should have to be a larger size. But even with lower kernel sizes, you can use more number of filters to account for your lack of filter size, or to reduce the computational cost. So there's always this trade-off. So tomorrow I will go a little bit more in detail. But one aspect that I want to talk about is the specific area of research called neural architecture search, where this question often comes: how many hidden layers, how many neurons in a hidden layer, how many filters, what should be the size of the filter, what should be the activation function, and so forth. Neural architecture search is about, you can train multiple neural networks and specify an objective function and a criteria to decide on which model serves my purpose best. And then using that as a means, sample better performing networks, because those networks provided you better metric results. And you will be surprised to see that the network architecture that was found from that iteration may be completely different from what you were going for. So I provided a link over here in TensorFlow with this library called Optuna. You can do that by specifying an objective function. And internally, they have all these different methods to look for the right neural architecture search. They can look for Bayesian optimization-based methods in which they keep track of better performing models in the area of hyperparameters that performed better, in the sense that they had better validation accuracy, or any specific metric that you have specified in the objective function. You may also opt for evolutionary methods such as genetic algorithm, where they have a fitness function, and all of these population here, each population item is a neural network. Whichever performs better on that fitness function gets to evolve further by cross-population with other neural networks, or mutation with other neural networks. So that this concept of evolutionary methods comes a little bit from biology and genetic propagation, gene propagation, and so forth. So you please feel free to read more how you specify your neural network and how you specify your objective function, so that, yeah, this is the objective function that I was talking about. And in here, you create the model and you create an optimizer. And here the metric is accuracy. So this objective function will look for models which tries to minimize maximize the accuracy in each trial. Yeah, does that answer your question?
Yes, Dr. Shubhajit, that clearly answered the question. We have one more question.
Yeah, sure.
Are nonlinear filters and pooling operations the same?
No, the pooling is essentially you're trying to capture some summary statistics from the results of your filtering operation. So pooling can be, you want to take the maximum value out of your results from your filtering operation, or you want to take the mean value. And I'll go over that a little bit more detail in tomorrow's session. In pooling, we do not train we do not train the numbers in the pooling layer, but we train the filter. So those are different things.
Dr. Shubhajit, can I add a little bit here from my understanding?
Sure.
Yeah, so the nonlinear filtration that we saw today, that is an engineering way to do image processing. And with convolutional neural network, we are automating it and making the network learn itself how to filter the filter an image. And pooling is a part of it. So what I understand, Shubhajit, from your session is those filters are in the conventional or traditional engineering approach of image processing, and pooling is its counterpart in an automated way of doing it, which is with deep learning CNNs. Is that correct understanding?
Yeah, and also I think pooling also helps you regularize your training because you do not want to memorize your input data, but you want to just summarize your input data. So pooling kind of gives you summary statistics in the sense that maximum, minimum, or median values. If you do not use pooling, your network will learn everything that is the output of the filtering operation.
Yeah, thank you.
Yeah. Any other questions?
Yes, Dr. Shubhajit, we have one more question.
Sure.
Please explain the difference between theory and model.
So this is a very high-level question. I'm not sure how to take it. So theory is, to me, the understanding and the mechanism of how machine learning algorithms work. Model here, in the sense of when you're deploying, may mean a specific class of algorithm that you're talking about, let's say a neural network. What are the specifications of the neural network? What does the model entail? Does it have weights and biases? And what are the parameters and so forth? Theory, on the other hand, is more on how a certain task has to be performed. So what is the logic behind it? What is the method behind it?
Thank you for answering that, Dr. Shubhajit. We do not have any more questions from the audience yet, so we can move ahead.
Okay, so I think in the interest of time, I'll just quickly run through this notebook. Here, I'm performing the same task of image classification on the same Mnist data set. Like I showed, there's a lot of parameters that you may want to tune. But in this case, this model is not a dense network. There's a CNN. So you see these Cond 2D layers. You do not have to worry about what they are now because I'll go over these in tomorrow's session. But what I wanted to show here was that in the training, we got very good accuracy on the validation set, which is 98%. This is the data set that we were training on. This is handwritten digits from 0 to 9, and we're predicting the label for it. Then we augmented the images, meaning that we added some noise to it, rotated some of the images differently, shifted them, added shear to it, or zoomed in some of the images. And when we augmented it, we looked at what they looked like. So you see some of them are rotated, some of them transition to a different location. And then using the same trained model, when we evaluate it on the augmented data, we see the accuracy drop to 34%, meaning that the original model never got to see this kind of images, this kind of augmentation, this kind of transformation. So what I do is that I retrain the model with augmented data, and then I test for the performance. And I see now the performance has improved. And this is the logic of data augmentation for images, because in real world, your images will not be as cleanly taken as you would in your very nicely curated data sets. People may take images of a bag, and half of the bag is not even on the image, or maybe it's rotated or tilted or flipped. Your model may not be trained to know that it's a bag because it has never seen that in the training set. So that's why you need data augmentation. So in this simple use case, when we did augment the data in the training set, we were able to improve its performance on the test set. One other aspect that I want to talk about of TensorFlow is Tensorboard. Tensorboard is essentially a visualization plugin which helps you further probe your model. So I have already created this Tensorboard using the callback function. And when I open it, it shows me the performance results per epoch. So there was total 10 epochs, and the accuracy was 97 in the beginning, and towards the end it was almost 99%. Here it shows how the loss came down. You can also look at your model. What are the different layers? How these different functions piece together? What is the data that is being exchanged between different different components of that model? So you can verify your model architecture. And then there is some weights that are learned in different layers. You can also probe that, what weight has been learned, what is the bias, and what are these kernels, what do they represent. You can also do that. You can also look at the distribution of the values. So here that was between minus 0.04 to 0.04. So this is for your ease to understand what the model has learned, what are the parameters, what is the architecture of the model, to experiment on your model design. And like I said, neural architecture search is a big area. So this kind of visual interface helps you further probe which model is suitable for the task, because there could be like many different versions of it. So I'll pause for some other questions. Other than that, I think I have covered most of it, except for the TensorFlow 101. If there is no question, I can just go over that quickly and summarize my presentation today.
Dr. Shubhajit, we do not have any questions from the audience yet, so we can move ahead with the session.
Okay, sure. So let me share my slide. Do you see the slide?
Yes, Dr. Shubhajit, it's visible.
Okay, great. So I'll move on to, TensorFlow. So TensorFlow, you might have just seen a very high level overview of what TensorFlow is. It is a library to model deep learning models by Google. The basic data structure is tensor. It's essentially multi-dimensional arrays or lists, very similar to NumPy. There are various data types that you can store in this multi-dimensional array called tensor, like floats of 32-bit or 64-bit, or integer, or string and bool. You can compute the rank of your matrix or shape of the matrix of the data type, just like you would do in NumPy and others. You can also add matrices together. You can multiply them. For example, here I'm doing tf.matmul, which is matrix multiplication. I'm adding in matrix 1 and matrix 2. You can also compute other properties of matrices like determinants and so forth. One important thing in TensorFlow is that what separates it from other libraries like NumPy is that it creates a computational graph, meaning that all the operations that you do are represented as nodes in the graph, and all the data that is exchanged are the edges, and the data that is exchanged are tensors. So a graph, computational graph that of your operations may look something like that. Your first operation may be addition, and you're bringing in two tensors. One has data 15, another has data 2, and you add them, and the output is 17. And the next operation is multiply. And let's say you multiply with something with 200, and the output of that goes to another operation that is division. And then finally, this is your end of your steps. So this is your final end result. So this is the computational computation graph that is built. So there are two kinds of data types in TensorFlow. One is constant, which is just data. There's nothing else. Another is variable. Variable is a class in TensorFlow. And that means that it has trainable parameters and it computes gradient. So in the yesterday's session, Dr. Chita talked about backpropagation and taking the gradients of the weights to understand how much the weights should be updated in each iteration of gradient descent. So a computational graph in TensorFlow automatically does that for you. So you do not have to worry about backpropagation. So that's why you need TensorFlow for models such as deep learning. This is something that is not in NumPy. But within TensorFlow, the data is saved and stored as a NumPy array. So you can always call retrieve the data by calling in .numpy. So any tensor .numpy gives you the data within it, but it also has other components like the gradients and other computational graph related information, like which other operation is it related to and others. I think I already talked about data augmentation. Essentially, real world data is quite different. Often in many problems, data is not available because the event is so rare. Diversity in training data is extremely relevant. The in-class imbalance is one of the major problems in machine learning. So for most of these problem scenarios, people use data augmentation or sometimes use GAN models, which synthetically generate new data. So these are some of the mechanisms we learned today: cropping, rotation, adding noise, or changing the color scheme. There are some others like flipping, scaling, and translation. All of this goes together. So in TensorFlow, you do not have to do all of that manually. There's a image data generator class, and in that you can specify for example, rotation range. So it will randomly rotate your input training data within this range of 30. You can specify width, shift of the width within this range. You can specify a range for the shear or the zoom and others. So all of these will be randomly sampled, and your data will be augmented for you. And you already saw in the simple example that it led to a better performance. These were some of the visualizations that I already talked about. I'll not go over these. So in summary, what we learned today was image data fundamentals. How can we manipulate images with popular libraries such as Opencv? More specifically, learned about convolutions and filters. We saw application of image data on machine learning, both with and without data augmentation. And I showed you a very brief high-level overview of TensorFlow that we will also use again tomorrow. In the next session, I'll talk about image classification, such as CNN with CNN model and various types of CNN model like AlexNet, VGGNet, GoogleNet, and what are the differences between them and how they innovated on top of each other to improve performance and reduce computational cost. I'll also talk a little bit about object detection and provide an application with a demo of both classification detection. With that, I end my talk and still will be happy to take more questions or feedback.
I can't thank you enough for this session, Dr. Shubhajit. You have synthesized such complex information in an easy to understand content. I have my curiosity aroused for the field of image processing now. I thank you again for sharing this information with all of us. With this, we can conclude day 4 of our workshop. We do not have any further questions from the audiences, Dr. Shubhajit. Thank you so much for your time and for sharing all this content with all of us.
Great, my pleasure, and I look forward to listening, talking more tomorrow.
Definitely, we look forward to having you tomorrow as well. For the audiences, the feedback link has been shared in the chat and on the Telegram group. The study material for day 5 and tomorrow's schedule will be shared in the email with all of you. Thank you for joining. See you tomorrow.